All right, so I'll spend most of the day talking about the various techniques, design decisions, architectural patterns that we use to build a system that is both cloud native, but still supports the traditional SQL semantics that you would expect from a SQL database. Before we get into that, though, I want to first lay down why this sort of system would be interesting, why it doesn't exist, and why it would be great if it did exist. And so why would you want a cloud-native SQL database? And you all know what cloud-native means, but specifically for databases, what's important is that it's horizontally scalable, and it can handle and recover from failures automatically. So if you think of traditional SQL databases, going back to Postgres or MySQL or all the proprietary solutions, they typically run on a single machine. You might shard them, or you might set up master-slave replication, but they're typically built from the ground up to run on a single machine. And that single machine becomes a single point of failure. And it also limits your ability to scale up as you want to store more data or process more queries. You have to buy bigger and bigger machines rather than just adding more machines. That's a real limitation from an operational perspective. So a cloud-native database is one that can survive failures, scale out horizontally, and is really easy for the operator to manage. And this describes a number of existing databases. It just turns out that they're all NoSQL systems. So you think to all the NoSQL databases you know and love, most of them have these horizontal scalability and failure recovery properties to at least some extent. They can replicate data. They can spread across data centers for some of them. But they're all lacking a couple of really important features that SQL databases have traditionally offered to developers. And that's going back to consistency in transactions. So when you're using a SQL database, developers get this nice benefit that they can trust the data in it is all up to date. There's nothing stale. No replication is clobbering data. You can trust that transactions won't interact with each other in bad ways, so that everything you write and read from the database is consistent and safe. And this makes writing systems significantly easier if you can rely on these properties. If you've ever built a system that uses a NoSQL database, you probably spent some time up front having to design around this. So if you can think back to your experience, you might have ran into bugs while you were operating it due to stale data or due to your application crashing in the middle of a multi-step operation. These things cost a lot of developer time, a lot of developer effort, and also cause bugs for customers. So Google created a system called Spanner that many of you have probably heard of that was the inspiration for CockroachDB. And Spanner, in the paper justifying it, the authors of the paper wrote that we'd much rather have developers occasionally looking into latency problems caused by using transactions too much than to have those developers have to work around the lack of transactions all the time. It's much better for Google as a business if their developers don't have to worry about the lack of transactions and if they can just trust that the database works the way they expect. So they went to this huge expense of both building and operating this system and found it to be more than worth it for everyone to start using it. And I think the same thing is true of a lot of systems out there outside of Google. They don't have this available to them yet, but they would have a much easier time building and maintaining their applications if they could trust on their database to provide them with more guarantees. And it would be great if more systems provided consistency in transactions. But when NoSQL databases came around, the fundamental motivation for building them was availability and scalability. You had these large web-scale companies trying to run massive distributed services that couldn't work with just a single machine database backing them. They needed to be able to stay up all the time, to scale out across multiple machines, and to survive all sorts of failures, because these systems need to be up all the time, or else the companies are losing money. And so it's not that the people developing Bigtable or Cassandra or Mongo back when they did were throwing out consistency in transactions because they didn't think they were valuable or because they thought they were too confusing. It was purely a matter of prioritization, that it was too hard to package them into the database, and they thought availability and scalability were more important, which has absolutely been true. A lot of great systems have been built on top of these databases that don't have consistency or transactions. It's powered a lot of powerful businesses. But those businesses and those services would have been easier to build if they could have relied on their database a little bit more. And so when you're choosing a database today, you have to make this choice. You're picking between multiple options. You're making a trade-off. You're either picking a SQL database that is great for your developers, but probably tough on your operations team, who has to deal with this lack of horizontal scalability. Or you're picking a NoSQL database, which is easier to operate in some ways, but is a lot tougher on your developers, who have to make this extra effort to build around the database's issues. And that's where CockroachDB is trying to come in. That's why we're building this new system. We want a database that's scalable, that can survive failures, that is strongly consistent, and that gives the standard SQL interface that everyone is familiar with. And it's all being built out in the open and open source. It's out on GitHub. And we think that this is something that will make building applications easier for everyone, while still making the database easy to operate for your reliability teams. And so I'm going to talk most of today about how the system works. So how you can build a system that replicates data, that scales horizontally, that survives failures, while still providing consistency without having to sacrifice performance. And so I'm going to focus on three main areas, kind of starting from the core of the system in terms of how data gets spread around a cluster of machines, then getting into how we keep that data consistent amongst them, and how we provide arbitrary transactions on top of that. And before we get into too much detail, it's worth understanding how the system is laid out. It's built as a series of layers where we have a SQL interface on top that the clients actually talk to. That SQL interface relies on a fully transactional, consistent key value store underneath it. So they're very separated abstractions, which helps development a lot. Sorry.
The question. So before you go to how, about what, so do you also provide replication and survivability over like distributed setup? So can you be distributed geographically over multiple continents?
Yes, you can be distributed geographically over very long lengths.
It has been battle tested.
It's still a beta product right now. We're hoping to go 1.0 in the next month or so.
Thank you.
Yeah, so the system is split up into a bunch of layers, where the transactional key value store can rely on this data being distributed across a bunch of machines, and can rely on that data being replicated consistently, and can rely on a solid layer that persists the data onto disk. So we're going to start by looking at this middle layer that tracks where the data is amongst all the machines in the cluster and keeps track of it so that when a query comes in, we know exactly where the data that it wants is located. And when you're working with a distributed system that is managing data, the first question you should typically ask is, how is that data split up onto the machines, and how do you find any given data that you want? Because that's very fundamental to how everything else within the system works. And so when you're asking how it's split up and how it's located, there are two approaches that have been used in a lot of previous systems, kind of as prior art. The first is hashing, which is seen in systems like Cassandra, where to find where a given piece of data is located, you hash the key using some hash function that's predetermined, and then use that resulting value to index into the machines in the cluster. And this is great because you know exactly where any given key is located just based on the value of the key. You don't have any sort of separate lookup structure. The problem is that because it's a hashing function, keys with similar values are mapped all over the place. So you can't do sequential scans efficiently at all, which is a real showstopper for a SQL database, which relies heavily on ordered indexes to do lookups and joins and queries. So we've had to go in Cockroach with what's known as an order preserving approach, which is great for providing efficient scans, but it requires an additional indexing structure. And it looks a little like this. So you take the key space, which is just the Unicode alphabet, and break it up into a bunch of chunks. So you pick arbitrary dividing lines that create reasonably sized chunks for your data. And we call each of those chunks a range, because it's a range of the key space. And so once you have that, you don't know where any of those chunks live, because given a key, you just know that it's in some chunk somewhere, but that doesn't tell you where it is. So you have to add this range indexing structure on top, which is a little more work than you need in a hash-based system. So this range index simply keeps track of all the different ranges that are in the system and what machines they're currently located on. And given that, you can do a lookup pretty easily by checking the index to find which range the key you want to find is in, getting the locations of that range within the cluster, and then going to ask one of those locations for the key. It also makes range lookups really easy because you just find the range where the start key is in and the range where the end key is in and read all the ranges between them. Another nice little perk of splitting up your data in this ordered way is that when you get too much data in a range, you can just split it in half. Pick some point in the middle, break it into two new ranges, and update your indexing structure in some consistent manner. In a hash-based approach, if you end up with too much data on one machine, you have to either add a bunch more machines so that the data falls elsewhere, or change your hashing function in some way, which can be a much trickier operation than just splitting a range in half. And so once you've split this range in half, they can each be managed separately, moved around to different machines independently.
And of course, we keep multiple copies of each range. Yes?
Do you handle sharding after the index was created? Can you shard it?
So all of this is within the system. It's invisible to the user. Data can be split up automatically by the system so that they're in reasonably sized chunks. The user can also request to have us pre-split ranges for performance reasons if they'd like. But in general, we'll split things when the data gets too large to be in a single range for performance reasons and availability reasons. And the index gets automatically updated all of the time when this happens, and it's all invisible to the user. Does that answer your question? So we need to keep multiple copies of everything because this is a distributed system. Machines can fail. We need to plan for that. So by default, we keep 3 copies of every range. You can configure it to be more if you'd like. And rather than having some external control process that manages where all the data is located, it's built into the nodes themselves. So each node is gossiping information about itself so that node 1 has some idea of how much data is on node 4, how many ranges that are there, how much traffic it's getting, et cetera. So if a new node joins the cluster, all of a sudden nodes 1 through 3 see there's this new node that has nothing on it. I have a bunch of data on me. I'm going to share some of my data with it to lighten my load and raise its load. So this is a decentralized process based on a gossip protocol. And it looks, it all happens in a very orderly fashion where a node will say, node 4, will you take some of this data off my hands? I'm going to give you my copy of this range. Node 4 will generally accept it and take it. And then node 3 can get rid of it, which lightens the load on node 3 and makes it that if a node fails, there will be less recovery that's needed. And similarly, this will continue happening until the replica thinks, or the system thinks that it's mostly balanced. So a second range will get replicated over there. And at this point, the cluster is mostly balanced. And the same thing happens if a node fails, just a little bit faster and more urgently. So if a node fails, then ranges 1 and 3 no longer have enough copies. So the nodes that do have a copy of them will quickly try to find a node to copy them to. So if node 2 fails here, the ranges that lost a copy will be up-replicated where there is space in the cluster. And at this point, the old node can just be forgotten about, and the system is rebalanced. And so this is always happening in the background. You're issuing queries. It's just happening separately, and it's done in such a way that it doesn't happen all at once and disrupt a bunch of user queries when it happens. It's done in a controlled fashion. So for all of this, we make the ranges about 64 megabytes in size, which is just an experimentally determined value that performs pretty well. It's kind of a fight between making them smaller, which makes them easier to replicate around the cluster and cheaper to do so, and cheaper to split into multiple halves. But you don't want to have so many ranges that your indexing overhead gets huge, because this indexing table has a bunch of entries, and typically the entries are cached on each node so that lookups are faster. And if you have too many index entries here, then lookups can be more expensive. The caches need to be bigger. It slows down the system a little. And so this method of splitting up data into ranges and distributing them around a pool of nodes has been in a bunch of pre-existing systems, most notably things like HBase or the Google databases. And that's how we keep data spread around the cluster. Are there any questions on that before I move on to how we keep data in sync? So let's take 1 or 2 questions here.
Cache, do you mean by in memory?
Yeah, so the index structure is spread around the different nodes in the cluster, but each node keeps a cache of where it thinks ranges are located, which improves performance on common lookups.
This is the only thing we keep in memory.
Yeah.
Like every single node in the cluster knows location of every single key.
No, so there are a couple. So this indexing structure is actually kept as a range in the cluster. So it's located on 3, 5, 7, however many nodes. And then when another node receives a request to do a lookup, it has to check with the index to find where that is. But as a basic optimization, keeps a cache of the ranges that it looked up recently.
Okay.
Yeah, go ahead.
What about data corruption? Do you do checksums?
Yeah, there are a bunch of consistency checksums. Why don't we move on, and I'll take more questions at the end on more general topics. So once you have a bunch of data in your cluster, as soon as you have multiple copies of it, the immediate question is what happens if they get out of sync, or how do you keep them from getting out of sync? Because when you only have one copy, it's really easy. You know exactly what the truth is. When you have multiple copies, they can get out of sync. One of them can get corrupted, as was mentioned. And so you have these multiple copies. but you have to keep them in sync. A traditional solution is to use a primary-secondary replication. This is what you see in most traditional SQL databases. Some more modern systems have started using what's called consensus. This is what's used in etcd, which backs Kubernetes. And primary-secondary replication is a very simple idea on the surface. The idea is that you have a primary node at all times. It receives all the writes. It writes its incoming requests to disk and sends them along to some secondary, which also writes them. It sounds great, but it has a lot of practical complications when you actually try to run it. And you have to deal with failures and all of that. So right off the bat, you have to choose whether you're doing your replications synchronously or asynchronously. If you choose the asynchronous approach, then the data on your secondary is potentially out of date. And if you're doing reads from it, you'll get stale reads. And if you have a failure, it might not have all the most recent data. If you're doing synchronous replication, meaning that your secondary has to acknowledge writes before the primary can acknowledge a write to a client, then you're lowering your availability by requiring the secondary to acknowledge writes. You're increasing your latency by adding a round trip to every write. And it's, again, very tricky on failover. It's really hard to get this right in practice. And so consensus tries to make this simpler in practice by making it harder to understand up front. You know, it's kind of flipping the tables a little bit. There's a whole bunch of consensus research that's been done. There you see systems like Paxos, like ViewStamp replication, like Raph. We use Raph in CockroachDB. And the general idea of consensus is that you're replicating to usually an odd number of machines, and something is considered committed when a majority of them agree that it should be committed. And so this is used in a bunch of modern database systems you see there. And it looks a little bit like this in Raph. A write comes into the leader. A leader is usually elected as a performance optimization so that all writes go through the leader, and you don't have to deal with multiple things proposing conflicting data. So at all times, a leader has been elected by the quorum. If the leader gets a write, it replicates it onto a follower. As soon as any of the followers have written that write to disk, the data is considered committed. Even before anything's been acknowledged, as soon as it's on disk, the data is committed. And then in the usual case, the acknowledgement will come back, and the leader can acknowledge the client. Notice that this runs as fast as the fastest quorum of nodes. If you have a couple slow nodes on the tail, it's not a big deal. So you can have two nodes running together in Germany, another node in Australia, and it doesn't matter if that third node is really far away. Your commits can proceed as fast as your two replicas that are closest together. So you can get really good performance on all your reads and writes in Germany and just let Australia catch up in the background.
Can you write two leaders at the same time? I mean, like you have whole AWS region goes down, yeah? And you have a leader in this region, number of queries were sent to the leader. What happens to them?
So this is fundamentally a CP system under the CAP theorem. So in a partition, the majority side of the quorum will be the only one that can continue making progress. So if the leader gets partitioned from the other nodes, its leadership, it won't be able to commit anything because it won't be able to get any acknowledgements. And its leadership will run out. And once it runs out, the other nodes can elect a new leader for the given consensus group and continue making progress on any writes or reads that they receive. And of course, in all these systems, the interesting part is what happens when things go wrong. And so if you have the same setup and a write comes in, but the leader crashes after it writes it to disk, then what will happen is that one of the other nodes will be elected as a leader. And so the second node here got elected as a leader. And it never got the key cherry. So the state of truth in this cluster right now is that cherry is not part of the system because only one of the three nodes has it. So if a read comes in for that key, the second node, the new leader, will be able to say that that key does not exist. And the node that has it will be corrected in the background. So the read that comes in for cherry will return that it does not exist in the system. And as I mentioned, we use Raph. We share the implementation with etcd. So they started it out. We've been contributing to it along the way. And it's really, really well-hardened implementation. We run one consensus group for each range of data. So in that past example with the three and four nodes, where we had 3 ranges, each of those ranges is a separate consensus group. And in a real cluster, since they're each only 64 megabytes, you can easily get thousands, tens of thousands, hundreds of thousands of these ranges, which is a lot of consensus groups to be managing. And that's where we differ from etcd quite a bit, because their whole system is one consensus group. So we have to have a bunch of engineering to work around this, to avoid overloading the network with all sorts of Raph background traffic. But Raph provides an incredibly solid foundation for the system. Even though there are some engineering complications involved in using it, we can truly rely on any write to a Raph group being atomic and durable It's either committed or it isn't, and once it's committed, it's pretty reliably there. So this is a great foundation for the system. The issue is that since we're doing a different consensus group for each range of data, we only get atomic committing for each range. You can't, without building something on top, atomically commit something that touches data in multiple ranges. So if you're writing the keys A, D, and Z, they're probably not all in the same range. We need to do something on top to make those separate commits, those separate transactions actually be atomic. And that's where the distributed transaction protocol comes in. And so this is something that's been built somewhat homegrown, somewhat based on research. It's kind of a mesh of the two. But the core problem is that we want to support traditional ACID semantics for SQL transactions. We need everything to be atomic, consistent, isolated from each other, and durable. We default to the serializable isolation level, which is the first isolation level that provides true isolation, that doesn't have any interactions between queries. This is actually stronger than some single node databases default to, which is kind of funny. And in order to do this, we can't just copy what single node databases do. We have different constraints. We can't rely on a single disk write to atomically commit something because we have multiple disks potentially spread across the world. We can't use distributed locking very easily because it's very expensive relative to single machine locking. And so the transaction protocol looks a little different from what you see in a single node system. Some of the things that we do to work around this are to rely on a raft group write being somewhat analogous to a single disk block write. So when a transaction comes in, we create a record for it. That record has some ID for the transaction, has its state, some other metadata. And when we do writes within the transaction, we tag the written data with that ID to indicate that it might not be committed yet. But if you want to check whether it's committed, go look up that transaction ID, see whether or not it's done. And then when the transaction finishes, we just mark that single transaction record, which lives within a raft group, as finished. And so that raft group write is atomic, and so that makes the transaction commit atomic. And as for locking, we have to use an optimistic concurrency control protocol instead, which effectively amounts to detecting conflicts as they occur, rather than using locks to prevent them from occurring. So we have to detect them and then abort one of the transactions or retry one of the transactions as necessary. And so I'm going to go through a couple small examples here just to give an idea of what it looks like. In the simple case where everything goes well, a transaction comes in, we create a record for it somewhere, usually on the same range as the first write for efficiency reasons. You can go write multiple keys that are on different ranges, and when you want to commit, you just flip that transaction record to committed. And so that makes all the data considered committed and durable. After the fact, we usually go back and clean up those writes that had a transaction ID attached to them, which makes later reads on those keys more efficient. But it's not needed for correctness purposes. And so again, that's what happens when things go well. The interesting part of the transaction protocol is what happens when there are conflicts and when things go wrong. So in a read conflict, a transaction starts and writes a key. Another transaction comes in and tries to read that key. And it sees that there's this transaction ID still attached to that written key, which means that it might not be committed. It has to go check that transaction record to determine whether the data is committed. So it goes up and checks and sees that the transaction is pending. And in this case, the read can ignore that uncommitted value and go on and commit. What's interesting here is that there are some timestamps involved here. So if transaction 2's timestamp is less than transaction 1's, it can't just go ahead, or it can just go ahead and read the value. But if transaction 2's timestamp is greater than transaction 1's is initially, it might have to push the timestamp back in time, because it'd be illegal to return that the key doesn't exist if a transaction later comes in and commits that key at an earlier timestamp. So with distributed transactions, the timestamps can get a little fuzzy, but we're able to manage the timestamps as necessary to ensure correctness. In a write conflict, we have two transaction records, both try to write the same key. So in this case, one of them is going to have to be aborted. Both transactions can't write the same key at the same time. In a single node database, the second transaction would just get blocked on the lock. Just like in the previous read example, the read would just get blocked on transaction 1's lock. But since we don't have locks, one of these transactions has to be aborted in order to complete successfully. So based on some randomly generated priorities, transaction 2 will decide whether or not to abort itself or to abort the existing write. In this case, it aborts itself, overwrites the key, and it then commits. And transaction 1 will come back and see that it got aborted. It'll either have to internally retry or return an error to the client telling the client to retry. But that's the gist of how transactions work. There are a lot of fuzzy details, but the core principle is let everything proceed, detect when something has gone wrong, and abort one of the transactions if something has become a conflict. And so there are a lot more details than what I've been able to cover in this talk, but we have a blog that's full of technical details if you're curious to learn more. And so these are some general techniques that we've been able to use to build a database that is very cloud native in the way that it replicates data, scales horizontally, doesn't care about individual nodes in particular, but still provide these real valuable guarantees on top. And so real quick, just want to mention how to deploy it if you want to try it out. In the interest of being cloud native, it's a single statically compiled binary written in Go. The UI is packaged in, so you can just hit a different port on the binary to get an admin UI that gives you all sorts of insight into what's running in the cluster. A client to open up a SQL shell is built in. Each node in the cluster is symmetric, so there's no special roles. You just spin them all up, and they're all considered equal. So there's no master that you need to protect. You can let any node fail. It doesn't matter at all, and it's just going to balance and heal no matter which one you get rid of. And so starting a cluster is super easy. Just run cockroach start on a machine. If you want to join more machines into the cluster, just start them up with the address of any of the nodes in the cluster. And they'll connect, gossip their information, and join the consensus groups. We have a Docker image. We have a Kubernetes configuration. We have a Helm chart if you're into Helm. We use a stateful set with Kubernetes, along with things like pod disruption budgets that got added in 1.5 to ensure that automated upgrades won't take down too many nodes at once. These configurations are all fairly solid. How much time do we get? It's 3:10. Cool. So I'll skip a demo and leave some more time for questions if you guys want to ask me anything. Yeah. Thank you, guys. Go ahead.
You said all the writes have to go through the master.
All the writes go through the leader for the range, yes.
Do all the reads have to go through the leader? And if not so, do you have a problem with timestamps across the master?
Yes, so for correctness, reads do have to go to the current leader. And actually, it's even a little stronger than that. They have to go to what we call a current leaseholder, which is a mechanism built on top of Raph. Because otherwise, without this extra safety that we add in, even sending all reads to the leader would be sometimes incorrect unless those reads also go through Raph, which is an issue that's come up with a number of systems, including etcd. So reads do have to go to the leader. There is some work that we're interested in doing in the future using something called egalitarian Paxos, which would enable things to not all have to go through a leader. But for now and for the foreseeable future, everything will have to go through the leader. Yeah.
Can you just sum up the latest Jepson test findings that you did with?
Yeah. So Kyle worked with us last fall and ran a whole bunch of tests against us. He found 2 bugs that he was able to generate inconsistencies with after tons and tons of pounding, and they were both logic errors that better unit testing could have caught. And so after those 2 bugs were fixed, he wasn't able to find any true faults. So at this point, there's no known consistency issues. So he was testing the fact that transactions are serializable and that all data is consistent. And so the results were really great there, other than those 2 bugs he found. In the back.
Yeah, could you go just a little more detail at a high level why this doesn't violate the hash theorem?
So it is a CP system. We're not claiming that during a partition, all nodes will be able to make forward progress. If you have a partition, the larger side of the partition should be able to make forward progress. But anything on the smaller side is unlikely to be able to do so. So it's fully a CP system, but by replicating data, we make it so that individual things going down doesn't hurt availability. If you're replicating your data across data centers, entire data center failures won't bring your system down, but it's still technically a CP system.
Because traditional logic was these Yet you're finding a niche that says, well, yes, we can make an SQL database do that.
Yeah, so things like Raph have made this much easier than they would have been 5 years ago. Because previously you'd have to try to implement Paxos, which is a very tough task. But now you can find a good implementation of Raft in all sorts of languages and build a system based on that. I mean, there's a ton of engineering involved, but it can work as a system if you put in enough time and optimize it right.
It seems like, given the architecture, that a join between two large ranges would be really, really slow.
Yes. So that's something that we've been working on a lot over the last 6 months or so. It's what we're calling distributed SQL, where we basically take SQL queries that are touching a lot of data and turn them into something akin to a MapReduce, where we farm out different parts of the query to different machines and enable it to all happen in parallel. It's still slower than on a single machine, of course, because we are moving large amounts of data across the cluster. And we offer a feature called interleaved tables, such that if one table has a foreign key constraint on another table, you can actually interleave it underneath the table that it has the foreign key constraint on, so that joins on that foreign key are very, very cheap, because the data is all co-located within the same range. So that can help with certain use cases. But in the general case, yes, joins can be slow, even with the distributed SQL. Yeah.
Quick question about adding and removing nodes. Do we have some kind of locks?
Yes, so all adding, for nodes or for ranges? Yeah, so for adding nodes, adding a new node is pretty simple because when you add a node, it has nothing on it. And so it just introduces itself to one of the nodes in the cluster and gets information about the cluster via that gossip network. And once it's in that gossip network, other nodes will start giving it data. Splitting a range to create a new range, or creating a new range from scratch, has to go through the Raft consensus protocols to ensure safety. And so etcd similarly has logic in the Raft implementation for adding new members or moving members in a safe way.
Do you have any figures about scalability in terms of writes per second, transactions per second, and how they scale in terms of number of nodes?
Yeah, so it scales linearly. We've done testing on that up to 64 nodes, where adding each new node adds a linear amount of additional write and read throughput. Are you looking for absolute numbers? Depend a lot on what your workload is and on what kinds of machines you have. But we've hit 100,000 QPS on a recent YCSB test, and it does scale linearly as long as you're not adding more and more contention as you scale up. So in the back.
Do client applications participate in gossip so that they know which node to go to for their data?
So they don't currently. It's something that we could add with a fat client, but right now we're just expecting users to use their existing Postgres clients. We support a bunch of common ORMs.
So if the node that you're configured to go to goes down, then that client can't connect to the database anymore either?
Yes, so connecting through HA proxy or something like that is recommended so that you can connect to any node in the cluster and query for any data, and that works. But if you are connected to only a single node, then that client stops working as soon as that single node is unavailable, yeah.
Do you support transactions updating multiple ranges?
Yes, yeah, absolutely.
Because from the description it looks like, aren't they very likely to be cancelled if they, the more ranges they update, the more conflicts are going to happen, and then they will never be able to finish because they cancel.
So highly contented workloads don't work great in the naive design. We've added some optimizations here that add some amount of weighting, kind of simulating locks, such that if you're blocked on something that another transaction is currently writing to, that it will wait for a short period of time before aborting. And this has drastically improved performance on highly, highly contended workloads. And that was one of the issues in the Jepsen testing, was that Afir was hammering single rows with all of his writes. And so they were all waiting on each other, being aborted. But adding the short waiting period drastically improved the amount of retries and throughput that was able to be done. In the back?
It's fire compatible with Postgres, right?
Yes.
Are there any limitations to that? Would you recommend migrating a database from Postgres to
We would definitely recommend migrating from Postgres to Cockroach. That's one of the big benefits of using the same protocol. So we don't support every last feature. We've had a big push to make ORMs work, the object relational mapping libraries that are in a bunch of languages. And some of them use some very obscure edges of Postgres. And so we've been, over time, adding more and more of those edges, but we certainly haven't hit all of them yet. So we expect most applications to work, but it's very possible you'll hit a feature that we have not yet implemented, and we hope you'll tell us and we implement it. Usually it's not that big of a deal to throw them in.
Upsert and window inquiries would be a pain.
Yeah, so we have upsert and we do have window inquiries, but yeah, they are some interesting features.
So if we would bet on CockroachDB, we know you're still there in 3 years. Do you have a model to earn money from it?
Yeah, so we've received a bunch of funding, but announced a couple months ago what our main business model will be, which is that while almost all of the product is Apache 2 licensed, certain features that we don't think any startup would ever need, that only enterprises would need, are going under a separate license. So they're still open source, but they're under what we call the Cockroach Community License. And so these features that have been planned right now are distributed backup and restore rather than single node, like a slightly slower backup and restore that's widely available, and then per row geographical placement of your data. So right now you can configure where your data lives on a table level. So you say this table lives in these data centers or in these countries or whatnot. At the enterprise level, you can do that on a per row basis based on certain columns in your rows. Yeah.
I was trying to migrate the Postgres application using Cockroach, and the first thing that was running me using sequences.
Using what, sorry?
Sequences.
Sequences. Yeah. So
What's your recommendation?
I don't have a good answer for you right now. I spend most of my time in the core rather than in the SQL layer, so I'm not super familiar with sequences. But I can talk to you afterwards if you'd like. Sorry. Yeah.
How much do you rely on the time on the nodes?
So
Break or just slow down?
we rely much less than Spanner in the sense that we use a different commit protocol. So Spanner's commit protocol requires very, very low latency, like single-digit millisecond latency for commits to perform well. We allow up to hundreds of milliseconds, even a second, of clock offset between nodes, depending on your environment, still with good performance. But if your clock offset between nodes exceeds the pre-configured amount, we will kill one or more of those nodes processes to avoid potentially inconsistent reads that can happen if clocks are incorrect. So we are constantly detecting the clock offset between nodes and will kill a process if it gets to a dangerous level. All right, thanks everyone.